At this point, I want to introduce Jason Forney. Jason is an architect and a senior associate with Brunner Cott Architects and Planners in Cambridge, Massachusetts. He's leading a design team focused on high levels of environmental sustainability in their work. His firm has recently completed a LEED Platinum and Gold level projects at Harvard, MIT, and here at Dartmouth, Lesley University, Vanderbilt University, and Macalester College. Jason was the associate in charge of the McLaughlin Cluster Residence Halls project here at Dartmouth, which opened in 2006 and has been a very successful project in a number of ways, most notably in terms of user satisfaction. My students love living there. He'll be speaking about low energy building and renovation, the business case. Welcome, Jason.
Thanks, Jack. Okay. Help me out here. Okay. So it's good to be here to talk to you today about low energy buildings, why they make sense, why we can do them now, and why they're really the next, or the first big step towards the net zero energy buildings that you just heard about. So I'm going to show you a set of 6 buildings that our firm's designed. 3 of them are new buildings, 3 of them are renovations, and talk about the common strategies across that set of buildings that allows us to get high PX buildings, I'll say. Low energy, high PX, sort of the same thing. And I will be talking about a lot of numbers because I think that measuring results is very, very important. So perhaps the first reason for doing this is if the cost of not acting is perhaps the biggest cost. If you look at my city of Cambridge or its buddy Boston across the river, you know, if we keep going with business as usual, what's going to happen? As most of the scientists who study oil production agree that we may have passed global peak, how are people going to behave when oil costs $200 a barrel? We need to start thinking about these things now. So luckily, I think there is an opportunity, and I'm a fairly young architect. In 2030, I'll be closing in on 60, which I think is the midpoint of an architect's career. Is that right? If we look at some numbers, this comes from Architecture 2030 and the Department of Energy. There are roughly 300 billion square feet of building, commercial building. Actually, this is commercial and residential in America. Over the next 30 years, 52 billion square feet will be demolished, and 150 billion square feet will be renovated. On top of that, 150 billion square feet of new building may be constructed. Now, these are very rough based on what's been happening over the last few years, but it gives you an idea that there's a tremendous opportunity, an opportunity that Ed Mazria calls historic opportunity, to impact a lot of buildings. Now, I think that maybe the renovation number might be higher, and maybe the new building number might be lower as certain things have happened over the last few years. And maybe we'll impact those existing buildings for the sake of purely improving their performance. So to take advantage of this opportunity, we really have to measure what we're doing. And there's an architect in the room here who I've heard say that architects need to understand energy consumption per square foot in the same way they understand cost per square foot. And so we need to know that hospitals and, well, first let me talk about the metric here. The metric, which you heard Malcolm talk about, is 1,000 BTU per square foot per year. And for those, I'm sure most of you are familiar with that term, but if you're not, I'll define it briefly. Taking all the energy that goes into a building, whether it's electricity, natural gas, wood pellets, and heating and cooling energy, converting it all to BTU, 1,000 BTU, and then dividing it by the square foot. that allows us to compare different sized buildings to each other. So we need to know, again, that hospitals, labs, food service buildings use a lot of energy. Campus building uses about 120. And I'll start referring to this kBTU per square foot per year as EUI, which is energy use intensity. It's easier to say. Average building, 90. And net zero, of course, is 0. So as we start to think about how to move from the 90 of the average building towards 0, there are several ways we can do it. To demonstrate, the business as usual way would be to take a building, a 3-story building that uses the 90, with an EUI of 90, costs $3 to build, and you add some PVs to it to get it halfway. And then you add some more PVs to it, get it to 0. Or you can take that same $3 and build a building that makes more sense, that considers energy as a design criteria, and use half or less of that energy, such as one of the buildings at McAllister College that I'll show you shortly. Then you can add $1 of PVs to that building. And so you've gotten a net zero in a much more intelligent and less expensive way, I would say. So moving towards net zero, we first have to reduce the loads, and that's the point that I'm trying to make today. I would say, and I'll show you through this set of buildings, that we can achieve 50 to 75% reductions over the regional averages that 2030 challenge targets. And that translates to a 35 to 60% reduction over codes that are in place now, energy codes. So quickly, that path that I'm describing roughly mirrors the 2030 challenge, where as the end of last year, to subscribe, your building was to use half the energy of a regional average for that type, and every beginning in 2010, 60%, and then 10% every 5 years, all the way to 0. And this follows that path that some of Malcolm's diagrams were looking at, constantly improving performance. This is the set of 6 buildings that our firm has designed over the last 9 or so years, actually beginning with the McLaughlin cluster here on campus. 3 new, 3 reuse. And I'd like to walk you through the performance data here. So the first building at McAllister College is an academic office and assembly building. We calculated the campus average with an EUI of 150. The other 2 buildings are dormitories, one the McLaughlin cluster again, and the other a residence hall at Lesley University in Cambridge. So when we created energy models of those buildings, this is what we found. More importantly is measuring the real performance. And we have measured the first 2. And the building here, we've been able to get good numbers on the electricity, but not necessarily on the heating and cooling. I think you might hear a little bit more about that later. So those are some pretty significant reductions, and I would say at the same cost as a regular building, as the budgets that these buildings would have had anyway. When you translate that to code, the codes are a little better than regional averages, but still pretty significant reductions. I'd like to talk about the 5 broad strategies that got us there. First is integrated design. After all, that's part of the name of this conference here, this symposium. Traditionally, we have thought about buildings using systems to solve one problem at a time. And by getting ourselves all together in the beginning, I'm sure most of you have worked in this manner, we can re-examine those systems and look at how they might do more than one thing at a time. For example, the residence halls up the street, the precast plank structure is the structure, it's the ceiling finish, and it also, in essence, becomes the mechanical system because there are radiant tubes running through it. Design with climate, you've seen these words before today. On the McAllister building, we decided on the very first day with all of our consultants in the room that the offices would be on the south facade, so they have a determined relationship with the sun to balance daylight heat loss and heat gain, and that we would block the wind on the north, and that we would limit the window-to-wall ratios on each facade. This built McAllister College is in St. Paul, Minnesota, which has about the same, it's about the same cold as it is here, but it has a summer like Boston. Shading is important, and shading is different depending on which facade you're working on. The south facade, straight overhangs work. On a west facade, you have to get more thoughtful with things like slanted vertical fins. We are in a cold climate, and all of these buildings are in cold climates. So I'd say, other than integrated design, the second most important strategy is envelope. So we began with insulation. All three of these buildings are 3-inch spray foam systems outside the sheathing, except that the McAllister building has also 5 inches of foam on the inside of the stud cavity, getting it closer to an R40 wall. The other two are just above R20. And the other important piece is that insulation is all continuous and not broken. Air tightness is another piece of the envelope that architects and builders are making huge advances in this area. It requires, to get it right, it's a code requirement in some states, including Massachusetts, but to get it right takes some serious work. We work with our builders to test the building during construction so that they can see where they're leaking. And perhaps the most important piece where things come together is at the windows, and you can see all the intricate work that has to take place around there. The insulation in this case is part of the air barrier system, and the McLaughlin cluster, we were able to scan those buildings infraredly afterwards and have the contractor go back and fix some of those areas. They did a great job. You can see those two sides are exactly the same, so why should one be different than the other? This can get very technical, and if anyone is interested in some of the hard data, I could talk about it afterwards. But the point here is that this building is 10 times tighter than the average commercial building in the United States. Daylighting. It's not hard. We have the tools to do it. We can build computer models. We can build physical models. And whether it's a diffuse skylight above a gathering room or tall windows in an office, thermal mass helps the building maintain an interior stability in terms of temperature, regardless of what's going on outside. Thermal bridging, as we build tighter buildings with more insulation, the weak points become more weak. And so whether it's decoupling the foundation wall from the first floor slab, or building an eave that's disconnected from the structural wall inside, or going extreme, people in Canada are making these kinds of brick ties with reduced areas. So those 5 broad strategies enable new types of mechanical systems, which is another aspect here. And we work with great partners in terms of engineers that have to be willing to engage in a dialogue about building envelope and design a system that works in a low energy building. Most often, in all 6 of these buildings, we decouple the ventilation from the space conditioning. In essence, there are 2 mechanical systems. One is for the ventilation air. Another one is to make it hot and cold when that's needed. Mostly hydronic because that's far more efficient than air-based systems. So we've chosen different systems in these different buildings. I've already talked about the radiant slab in the McLaughlin cluster, which is both a heating and cooling system. There are valent systems in 2 of these buildings, which is a different kind of system. It's essentially a radiator that goes up high on the wall, heats and cools, creates a current naturally without a fan. And in this building, a combination of systems in the McAllister building, in-floor systems and then suspended radiant panels that heat down on the occupants and also engage the thermal mass of the concrete structure above. So how does this change when you find a good old building that you want to reuse? Well, these are 3 buildings that we've worked on. One is complete, one is nearing completion at Hamilton College, and the other is Thayer Dining Hall just around the corner, which we're in the design phase now and beginning construction this summer. So again, those baselines, 90, 120, and 339, dining buildings use an extraordinary amount of energy, and that's a measured number from past year's data here. Predictions, and in the case of the building that's finished, measuring, I recognize some of the people here may have seen Harvard's presentation of how they, when they first started measuring the Blackstone building, the numbers were way off the charts. And through a lot of diligence and measuring and watching people's behavior, they were able to get the energy back down to the predicted number for last year. A good story in its own. So again, significant reductions. We can insulate old buildings. It takes a little more science and a little more thought to manage the moisture control of the walls. What we find that designers from the pre-war era were good at thinking about daylighting because they didn't have access to the cheap energy that we had afterwards. And then you can also cut holes in buildings to bring daylight in. These buildings often have a large amount of thermal mass. And that's a two-sided coin. It's good if it's inside the envelope, but what happens when it's outside? And those bricks, thick brick walls are exposed to 0 degrees. So it's a two-sided coin there. And we can also use these kinds of mechanical systems in existing buildings. So let's talk a little bit about the business case. And I like what Jerry Udelson says. If you're not building a green building, it's going to be functionally outdated the day it opens. And I'd like to walk you through the building. We were fortunate to work with a very good contractor, William Barry, in the Boston area on this building. And they're willing to share a lot of their thoughts about cost and in an open book way. So I'd like to go through this building, how we set the budget, what we think we spent, what we think we didn't spend on a mechanical system, and where we allocated those resources in a whole building kind of way. So we established a budget together with the contractor and the university based on comparable residence halls in the Boston-Cambridge area, based on cost per bed, not based on this is going to be a green building or a low-energy building. So once we have that target, then we can start to shift things around. So you take the systems that go into making a building, take some of the resources allocated to mechanical systems, put it into the envelope, put a little bit of it into general conditions so that we can test the continuity of the insulation and the air barrier, put a little bit of that into the electrical system so that we have daylight sensors. And then maybe finishes aren't so important in a residence hall, and we can have a more robust structure that gives us that thermal mass that we need. So at the end of the job, at the bidding process, one of the subcontractors volunteered to do a takeoff of what it would cost to go from the valence system that we had designed to the standard system for a dormitory, for a residence hall, which is a vertical stacked fan coil. And they just knew that it was going to be less. Turned out that it was $156,000 more. Plus it would require some drywall box outs and possibly a bigger boiler and chiller because we're delivering energy in a different way. So let's round that to $200,000. So then we asked, we sat down with the contractor and their estimating people and said, well, what did we do differently here? Where did we spend more money, and how does that compare to the $200,000 that we saved on the mechanical system? Well, 3 inches of spray foam is $34,000 more than bad insulation. We built a better air barrier that cost about $15,000 more, plus we spent some money testing it. We bought better windows, and we spent a fair amount of money on daylight and occupancy sensors. So in the end, we're still coming out ahead, and I'm sure there's things that we didn't remember when we were thinking about this. But the point is, if you have a budget at the beginning of a project, you can reallocate things within that budget to create a low-energy building. Then there's operating costs. If we're saving half the energy here, what does that mean over a longer period of time? So from Energy Star's Target Finder, a normal dormitory in that location, that zip code, same size, would spend $104,000 on operating energy in a year. So we've collected about 7 months of data on this building and can roughly tell that it's going to cost $65,000 for a year. Some of that, it's 50% of the energy, but where we're saving is mostly on the gas side. So electricity is more expensive, resulting in about $40,000 in a year. That adds up pretty quickly, and that's for the same first cost. So I'd like to leave you with three closing thoughts. While this is a big step, it's the first big step towards net zero, we do have to plan ahead. And so, for example, on this building, those are the plugs, the conduits for the future photovoltaics. We also have to remember, I was also very inspired by Dana's talk this morning, we have to think about, well, we have to sharpen our technical skills and our thinking skills with regards to energy. We have to be thinking beyond that. Buildings affect more than just energy there. There's an impact on human well-being. There's an impact on other resources. And so we have to think about all of these decisions as they affect these different things. And finally, we also have to keep doing the things that we've always done as architects. We can get very excited about this new set of tools, but we still have to make buildings that have their poetic moments and that are good places for people to be. Thank you. So I think we have 5 minutes. Yeah.
No? Yeah. Okay. Any questions?
Good.
Do you find that this approach is a marketing advantage to your firm in terms of differentiating yourselves against some of your competition?
Yes and no. I think with clients who can, with institutions and clients who can understand it, they may already be there anyway. And in that case, it is an advantage because we can speak a common language. But there are still clients who just don't believe that it doesn't cost more to build a green building. And it's taken a long time to compile this set of buildings. It's 10 years in the making. So we're really still into that effort, I would say, just beginning that effort of being able to have more than one building to talk about at a time. And I also think it's important that we have new and renovations because there are a lot of existing buildings out there.
So then only part of the market is interested in what you're doing. Is it accelerating, though? Is it growing?
Absolutely.
Got any idea how fast?
No. Not fast enough. But absolutely. I mean, I think this conference is an example. If there were 100 people here 2 years ago and there are 200 today, then maybe that's symbolic of how fast the interest has grown.
Okay. Thank you, Jason. Oh, Malcolm's got a follow-up.
I was just thinking of the medical Hippocratic Oath, do no harm. And it just struck me that we've seen, I think, that we have a choice about whether to do no harm with buildings or not, and yet we don't have the same kind of oath. So I sort of my question to the architects as professionals in the audience is Is that something that we should be thinking about trying to do in terms of changing our professional responsibility? And I can address it to the engineers as well. I mean, it's a two-way thing. But I think we really need to think about that.
Thank you.